Welcome to the deep dive. Large language models, LLMs, they've really shifted our expectations of AI, haven't they? They can write, reason, create. It's pretty amazing stuff. But here's a really interesting angle. Their true power, maybe their superpower, often gets unlocked when they're not just thinking alone, but when they can grab a tool, like searching the web or running some code. Think of them like these super smart assistants who suddenly get handed a whole toolkit. Today, we're diving into some genuinely cutting-edge research. There's this paper on RCEF called Agentic Reinforced Policy Optimization. Let's call it ARPO. And this isn't just a small tweak. It feels like a really novel way to train these LLM agents to get much better and maybe surprisingly way more efficient at using those tools for complex multi-step jobs. So our mission today, let's try to unpack this subtle challenge LLMs face with tools, see how ARPO cleverly gets around it, and figure out what its frankly impressive results mean for the future of AI agents that can actually do things. You might think, okay, an LLM connects to a tool like a Python interpreter or a search engine. Easy, right? It gets the info, processes it, moves on. But this is where the research gets really interesting. It turns out there's this kind of hidden but pretty crucial hurdle in how these agents are learning to deal with the outside world right now.
Yeah, what's fascinating is looking at how traditional reinforcement learning, the stuff often called trajectory level RL, usually works. Imagine you're teaching someone a complex puzzle. With trajectory level RL, it's like you give them the puzzle, let them try everything using tools, reasoning it out, and only when they're totally done, maybe hours later, you say, yep, right, or nope, wrong. That feedback, the reward, it only comes at the very, very end of that whole long sequence or trajectory. And while that's been foundational, it kind of falls short for these multi-step problems where the LLM needs to maybe use a tool, use another tool.
Right. It's not just one shot.
Exactly. It's like waiting until the final exam score to give a student any feedback on a whole semester's worth of homework and quizzes. It doesn't help them adjust along the way.
And why is that specific delay a problem, especially when the LLM is, say, halfway through solving something complicated?
Well, the core issue the researchers spotted is that LLMs tend to show what they call highly uncertain behavior right after they interact with an external tool. Think about it. The LLM asks a tool a question, gets some new info back. Sometimes that info is messy, maybe ambiguous, and the paper shows this sharp spike in something called token entropy right at that moment. It's like a measure of the LLM's confusion or uncertainty about what word to say next. Picture the LLM working on a tough math problem. It calls Python, gets a number back, and then it just kind of pauses, like it's frozen for a split second, unsure how to weave that new number back into its reasoning. It's standing at a crossroads with maybe too many ways forward.
Ah, okay, so it gets stuck momentarily.
Sort of, yeah. And this hesitation, this uncertainty, it's apparently much worse when the feedback is diverse text from a web search compared to, say, a clean, predictable number from a Python calculation. Figures 1 and 2 in the paper show this quite clearly. So what that means is that the old methods, the ones looking only at the final outcome, they often just gloss over these critical moments. They overemphasize complete rollout sampling, just comparing final answers, and they end up neglecting the exploration of fine-grained behavior at each tool use step. They miss the chance to teach the LLM how to handle that specific moment of uncertainty.
Okay, so that's the hurdle, this spike in uncertainty right after getting tool feedback. How did ARPO tackle this? How does it change the learning process?
ARPO's approach is, I think, really clever.
Sure.
Its main goal is to encourage the LLM policy model to adaptively branch sampling, specifically during those high entropy, high uncertainty moments right after a tool call. It's designed as an agentic RL algorithm, meaning it's really tailored for training these LMs that need to take multiple actions, use tools multiple times to get something done.
So it adapts its learning strategy on the fly.
Pretty much. A key part is its entropy-based adaptive rollout mechanism. Now, traditional methods often just do global sampling, trying out whole reasoning paths from start to finish. ARPO does that too initially, but then it keeps an eye on the LLM's real-time token entropy variation after every single tool use. If that entropy, that uncertainty measure, jumps above a set limit, the model doesn't just fail that path. Instead, it triggers additional partial sampling. It basically says, okay, this is a tricky spot, and it branches out multiple new potential reasoning paths right from that point of high uncertainty. Figure 4a in the paper has a great visual of this branching.
Ah, so it focuses the exploration effort right where it's needed most.
Exactly. It lets ARPO effectively expand the original sampling space, but in a targeted way. It balances learning the overall task, global, with learning how to handle these tricky steps, step level. And here's a really important bit. This makes it much more computationally efficient. Instead of scaling quadratically like ON2, which gets really slow and expensive fast, ARPO brings the complexity down, somewhere between ON log n and ON2. That's a huge deal for making training feasible.
Okay, that's the smart exploration. What else does ARPO do?
Well, to make the most of that adaptive sampling, it uses a technique called advantage attribution estimation. You can think of this as giving the LLM much more precise feedback almost immediately. It helps the model figure out what specific choices it made during that branched exploration actually led to a better outcome down the line.
Like a focus reward signal.
Kind of, yeah. It helps internalize advantage differences in stepwise tool use behaviors. The paper tried a couple of ways, hard and soft settings, and found the soft setting achieves consistently higher rewards with greater stability, which you can see in Figure 5. So ARPO just defaults to that more stable soft setting. And in one more piece, it uses a pretty neat hierarchical reward design. It's not just about, did you get the final answer right? It also rewards the LLM for using the tools correctly, like calling the function with the right format. And interestingly, it even gives a little bonus for multi-tool collaboration, like if it effectively used both web search and Python during the same problem-solving process.
So it encourages good tool-using habits, not just the right answer.
Exactly. It's trying to shape the whole reasoning process.
Okay, so putting it together, ARPO isn't just about random trial and error. It teaches the LLM to be smarter, to focus its learning, its exploration right on those moments where it feels uncertain after getting new tool info. That feels, well, fundamentally different, more intuitive somehow. All right, theory's great, but the proof is always in the performance, right, Grub? How did ARPO actually do when they tested it against other methods?
They really put it through its paces. We're talking 13 different benchmarks across three main areas: computational reasoning, knowledge reasoning, and these really tough, deep search domains. For the math and knowledge-based stuff, ARPO consistently outperformed all trajectory-level RL algorithms. Table 1 in the paper lays this out. It showed superiority across 10 datasets. We're talking an average accuracy improvement of 4% over other top RL methods. And importantly, these improvements held up across different backbone models, like both the Quinn and Llama series LLMs. So it's a pretty robust improvement.
Okay, solid gains there. But you mentioned depth search.
Ah, yes, the deep search tasks. This is where ARPO seemed to really pull away. These tasks are gnarly. They require digging through lots of web info, synthesizing it, using tools repeatedly and intelligently. They're so hard that even the really big advanced models we hear about, like GPT-4o and DeepSeek R1671B, apparently showed limited performance. But ARPO, even when using much smaller Quinn 3 models like the 8 billion and 14 billion parameter ones, it demonstrates exceptional performance. Get this. They reported pass-at-1 scores of 10.0% and 43.2% on the HLE and GIIA benchmarks. Pass-at-1 means I got the complex answer right on the very first try.
Wow, with smaller models, that's impressive.
It really is. And Table 2 shows these results. The researchers argue this really highlights how ARPO's algorithmic design, balancing that global view with the step-level focus, allows for diverse behavior exploration by LLMs during high-entropy tool use steps. It seems uniquely suited for navigating that kind of complex, uncertain information landscape.
Okay, performing better is great, especially with smaller models. But is it efficient? You mentioned efficiency earlier. Tool calls cost time, cost money in the real world.
That's a crucial point, absolutely. And this study found something quite remarkable here. ARPO achieves superior overall accuracy compared to GRPO, that's another strong RL algorithm, while using only half the number of tool calls.
Half the calls for better accuracy.
Exactly. Figure 7 shows this efficiency, and they attribute this directly to that entropy-based adaptive rollout mechanism. Because it's smart, it selectively explores branches only during high-entropy tool call steps. It's not wasting computation exploring paths where the model is already pretty confident. It learns more, but leaner.
That makes sense. Did they also look at the quality of the tool itself? Like, does it matter how good the browser agent is in those deep search tasks?
They did. Yeah, they ran ablation studies, basically, taking parts away to see what happens. Table 3 shows the results. And it confirmed that just relying on, say, rule-generated web snippet summaries is insufficient. You can't just give the LLM pre-digested bits. The study clearly found that the capability of the external browser agent is highly correlated with the accuracy of the deep search task. Using larger parameter browser agents, smarter, more capable browsing tools led to significantly better results.
Right, garbage in, garbage out. Even for smart AI, the tool quality matters.
Definitely. It's like giving a researcher access to a full library versus just a pamphlet. The better the resource, the better the potential outcome.
And the final big question for any new AI method, does it scale? Can this work as models get bigger, tasks get harder?
Always important. They did a scaling analysis of ARPO, which is shown in Figure 8. Looks pretty encouraging. Performance seemed to increase with uh, moderate entropy values, finding a sweet spot around zero point 0.4. This suggests, as they say, the necessity of balancing base sampling probabilities with entropy. Too much forced exploration isn't good, too little isn't good. Similarly, there seems to be an optimal initial sampling size to keep things balanced. But overall, the key finding was that increasing the global rollout size enhances model performance,
Which means,
which generally indicates the algorithm is scalable. As you give it more resources, bigger rollouts, it seems capable of learning more and performing better. That's what you want to see for future development.
okay, so let's wrap this up. We've taken quite the deep dive into ARPO here. It feels like it's shifting how we might train LLMs to use tools, moving away from just brute force trial and error towards something much smarter, more adaptive, and way more efficient, especially focusing on those moments of uncertainty.
Absolutely. I think this research really underscores a key idea, letting AI strategically explore its own uncertainty, especially after getting new information from the outside world, is crucial for building agents that are truly adaptable and genuinely powerful. ARPO seems to offer a practical, scalable way to better align these LLM agents with the kind of real-time dynamic environments they'll need to operate in to be truly useful.
It's a fascinating reminder, isn't it, that the next big leap in AI might not just be about more data or bigger models, but about the, I don't know, the finesse of learning, the efficiency of how they explore. So here's something to think about. As these LLMs get woven deeper into our lives, using tools almost like our own digital assistants, how might this idea, understanding, and even embracing uncertainty, right down at the algorithmic level, lead to AIs that aren't just more capable, but maybe more robust, more reliable, perhaps even more trustworthy, especially when things get messy and unpredictable?